All right, so just I want to make a little teeny tiny announcement is that about regarding office hours is that I show up to office hours at 7 o'clock, and if people don't come for the first 30 or 45 minutes, I'm gonna head out at that point. So the idea is if you want office hours, come at 7, and we can stay there for about 2 hours. But otherwise, I don't like waiting around for too long. So I just wanted to make sure people kind of knew that um, policy. Okay, I've got the chat open and I've got a picture drawn. I want to look at the members in the group. Okay. All right. So today we're going to be doing these a kind of integral. It's kind of integral along lines, and we're going to be integrating we're going to be sort of integrating a dot product along a curve. So here, before we get started, I'm going to kind of draw some motivation for you all. We're about to start moving into the third branch of the class finally, which is the most exciting and the most rewarding and the most beautiful. And they're regarding the fundamental theorems of calculus for higher dimensional calculus. And it's just really, really beautiful, cool stuff. So what we've got here is just pretend that I've drawn a map, and pretend you're some sort of air traffic controller or you're a pilot or something, and you've got city A and you've got city B, and the purple lines, the purple arrows sort of are representing the wind velocity at each point in the plane. So you can think of the wind. Wind is a thing that would be modeled by a vector field quite nicely. At each point, it's a direction and a speed. So imagine your job is to fly this plane from city A to city B. And I'll give you 3 options for paths that you'd like to take. So I'll call this is going to be, maybe you start here and you kind of go north a little bit and you eventually wind up east. Let's say you kind of go directly across the the x-axis. So I'll call this P1. I'll call this one P2, and then this one is P3. So these are your 3 options to get from city A to city B as a pilot, and you're trying to save on your aviation oil or your gas or your fuel or whatever that is. What you'd want to do is you would want to take the path of least resistance. You try to find a trajectory or a curve, a path that reduces how much you fight the wind. So as you can kind of imagine, traveling along P1 experiences the most resistance, the most wind resistance. Whereas down here, I guess I didn't call that P3. Okay, that's P1, P2, and that's P3. Whereas down here, P3 experiences the least. And today, what we'll do is we'll learn how to set up integrals that actually compute exactly as you go along a curve how much you've fought or gone along with an existing vector field on the plane. So today, the amount of resistance will be mathematically modeled by, I don't know if there's 2 L's in there. I think there are. I don't know. Okay, by the following integral. It's going to be an integral along a path or a curve or whatever. So I was calling them P's, but really it's an integral over some curve. And what are you going to be integrating? You're going to integrate some function ds. And that function is explicitly, so I'll take away those parentheses, is taking a vector field and dotting it with the unit tangent vector along the path. And that's the scalar, that turns out to be a scalar function, and you're integrating that with respect to s. So this turns out to be a scalar line integral because although you are seeing vectors on the inside of the integral, order of operation, you take those as a dot product, and that's a number. And so along the curve, you're integrating a number at each point. That's a scalar line integral. That's what we've had practice doing. So I'm going to erase that stuff. So this is a work or circulation integral. All right, now I'm going to zoom in on that picture a little bit up here and just kind of see what's going to happen. So, what I mean by that t is that unit tangent vector. So what I'm saying is, let's look along P1, that top curve. And so I'll draw a couple points. So maybe this point, and this point. I've got t, I'll do it in green. This is t, that's t, and this is t. And I've got, at each point, I've got the wind vector kind of coming this way. And in all three cases, you see I'm making an obtuse angle. And so along the black curve, as I accumulate these dot products, remember the dot product is negative for an obtuse angle. So I'm adding up along the curve, like I get a negative value here, I would get a negative value there, and a negative value there. And I would expect that the integral along P1 would be negative. And you can see as I go along the bottom, the opposite will happen, just how I've drawn the vector field. So as I move along at, say, 3 points, 3 arbitrarily chosen points, just to give a sampling, the unit tangent vector is moving in the direction of, or we're making acute angles here, and so we're really racking up positive values along our curve. And because we've integrating a positive function along a curve gives a positive number, we'll see that probably integral along P3 v dot t ds would probably be positive. And that middle one is 0 because I've made the vector field 0 along that curve. Okay, so that's theoretically what we're doing today. And this is on your written assignment. The last 3 problems are all setting up these things. So that's the setup. And unlike how we've done when I've introduced integrals in the past, I've set up the Riemann sum, and we've set up a Riemann sum, and we take a limit and we see what happens. But I think we've done enough of that, and that uses a lot of time, and we don't have a whole bunch of time. So I'll just kind of show you how to set this thing up without the Riemann sum. And if you're really interested in why it's that piece, you can look it up in the OpenStax. Okay, is it okay if I flip now? Okay, so really, how do we set up the circulation integral? Okay, this is an integral over c v dot t ds. So, well, what you have is, so c is parametrized, okay, by some r of t is x of t, y of t. You can do all of this for stuff in 3D as well. Everything works the same, but just for today, we'll just do the smaller examples in the 2D plane. Okay, so, and your t is ranging between some a and some b. It's also important that if you're doing the curves from a to b. So we're really working with oriented curves. C, okay, so C is an oriented curve. We want to go like it'll, there are arrows on the curve. We want to make sure our parameterization travels the right way. So C is parameterized by some r of t, and we have v of x, y. So the integral becomes, and well, okay, remember that the unit tangent vector at time t is the velocity, but you have to make it unit. That's this piece, then this is this piece, and then ds, we remember from, I don't know if it was last week or when, remember ds is the magnitude of r prime of t times dt. You'll also want to make sure that you're subbing in so that your integral is a function of t. You want to replace wherever you see x and y with x of t and y of t. So you'll have x of t, y of t, and the total integral is the integral from a to b. You're taking a dot product. So this is my red piece. You're dotting that with your unit tangent vector. So this is r prime of t over its length. So that was your unit tangent vector. And ds, which is r prime of t dt. This is your ds. And how do we know t of t? Joe is asking, where does we get this thing from? Remember, if you have any vector and you want to make it unit, you divide by its magnitude, and that's all we've done right there. And I'm not going to belabor this point too much, like why does it need to be the unit tangent vector? Why isn't it? Because if you really see what happens, there's a beautiful thing that happens. Look at down here in the blue and the green, we see cancellation. So in fact, a nice thing with line integrals, with circulation integrals, is unlike scalar line integrals, you don't necessarily need to compute the magnitude. You don't have to do that awful square root because of cancellation. Well, I'm not going to erase those. You'll get the integral from a to b of your vector field evaluated at your location with your derivative vector. And in fact, the deal is that t ds is really r prime of t dt. So there's kind of some cancellation that occurs, but this is really the formula that you'll use, that you'll be plugging things into. And again, it's kind of like a scalar line integral because you're integrating a function, along a curve. Again, you do have vectors on the inside of the integral at first glance, but they're taken care of by taking a dot product. You never want to like integrate v dt over c. That would be crazy. You need some dot products. You need to be dealing with some function. This would never ever happen. You would never do something like that. You need to be dotting it so you're getting scalar numbers. Okay, so let's do some examples on the next page, unless there are questions. Okay. So I'll remind you. I'll just write that formula, that the work integral is a to b v of x of t y of t dot r prime of t dt. So this is what we're going to set up. We'll do example 1. So we'll say, so C is the oriented line segment. Its r of t is 2 plus t, 2 minus t. Let's split that up. So you already know this is a segment. It's 2 comma 2 plus t times 1 negative 1. And I'm going to let t range from 0 to 2. And v, my vector field in the plane, is going to be negative y comma x. So before we even start doing an integral, let's sketch this picture out. get a guess for what the sign might be, and then check that our guess is correct. So I'm going to plot this out. We're in the XY plane, and this is X, this is Y, and I know my segment is, it starts off here, and it comes down to here. So it's this segment. That's my oriented curve C. C is just an oriented curve, just a curve with arrows along it to tell you which direction you're moving. And then I got to plot my vector field V. Okay, so that was the red. What's the green? The green, we've discussed this on probably on Monday, that this is the rotational vector field. It spins in the counterclockwise rotation. So V is kind of doing this. So can anybody eyeball and guess and like guesstimate what they think on average? Are we going along? Like, does the red fight the green, or does red go along the green? And if so, do you think the answer will, the total accumulation will be a positive or negative number? Fight. Yes, a fight against. Good. I like these responses. And so what do people think that the total integral might be, a positive or negative number? Negative. Yes. Okay, these are good. This is great. So we expect that the integral over C v dot t ds will be less than 0. So we can check this by, well, I've got the parameterization all set up. So we're going to be doing 0 to 2. That's from, I got that from 0 to 2 right there. Then I've got to take my green, so I'll actually do that in green. Well, negative y, I'll actually write this out. Negative y of t, comma, x of t. And I got to be dotting it. I guess I have to take my derivative, but that's not so bad. I can do that in a quick swoop. You can see that the derivative, that r prime, is just negative 1, comma, so nope, it'd be positive 1, comma 1. This is r prime of t, and then we got to slap on dt at the end. And that matches my formula at the top of the page. Okay. I just did that derivative really quickly in my head, where I just took a derivative here. Okay. And then let's start writing this out. Okay, this is my v. So this is now the integral from 0 to 2, and we're doing, okay, this is t minus 2, comma 2 plus t, dotted with 1, negative 1 dt. Okay, so you're seeing vectors on the inside of the integral, but that's okay. That's because there's a dot product connecting them. So in fact, we're going 0 to 2. I have to do that dot product, and I get t minus 2 minus 2 plus t, and that's weird. That's not what I got the first time, but that's fine. That's dt, 0 to 2, negative 4 dt, and that is just negative 4 times 2, and that's negative 8. So good. We did get a negative number. Yeah. We expect, okay, so we expected negatives because as I zoom in on the picture, yes, okay, we're kind of fighting. The red is fighting the green. Yes. All right. We're going to do 2 more examples of these, and then we're going to talk about something called Stokes' theorem, which is very pretty. Okay, so I'm going to move to this next page. Okay. So for the next integral, we're not going to have that green vector field. It's not going to be the rotational one. It's going to be our other close friend, which is the radial vector field. It's the one that looks like a firework. So here's example 2. I'm going to have v of xy is x comma y. It's nice to start, like at some point, I'll hope that you can look at this without needing to plot it and just remember that it's the radial vector field. Because remember, this is the gradient of 1/2 x squared plus y squared, which is a parabolic bowl, and to increase the parabolic bowl, you step outwards from the center. That's one way to think about it. In fact, okay. And then, so that's the vector field. We'll plot it with the curve. And the curve C is given by parameterization R of t. And this is going to be t comma t squared, where t ranges between 0 and 1. So it's nice when the problem gives you the parameterization from the get-go, because you might probably already get a feeling the parameterization is like half the work sometimes. So if they've given you the R of t, you're kind of in luck. All right, so let me plot our picture right now, and we'll kind of see what we've got going on. So in this case, my vector field emanates outwards from the origin. Okay, this is V. And my curve C, well, this is a leg of a parabola. And that is because you're looking at x is t and y is t squared, but t squared is just x squared. So you're really looking at y equals x squared, where your x is between 0 and 1. So this is a parabola from here to here, 0 to 1, and we're moving this way. So can anybody just take a guess? Can you feel it in your guts? Like, are we going to get a positive or negative accumulation as we go along? Positive, yes, this is positive, because just zooming in, like at this point, we'd be making acute angles at every step. That's right. All these angles are acute. So we expect, on the whole, a positive number. So let's check. We expect that this integral is going to be positive. So let's check. And this thing is the integral from 0 to 1, x of t, y of t, dotted with r prime of t. So I'll do that really quickly. We're taking the derivative of this, and that's 1 comma 2t dt. All right, now we're going 0 to 1. Remember, x of t, y of t, this is t comma t squared. If you're like, wait, that's weird, this is r of t itself. That's okay, that's because this vector field's weird. It's saying the x component is your x coordinate and your y component is your y coordinate. So that's why this thing on the left is exactly r of t itself. So that doesn't always happen, but this is a cool vector field. So this is 1 comma 2t dt. And if I do that dot product, I'm doing, I almost got coffee all over my laptop and not even my iPad, my advisor's iPad. Okay, then we do that dot product and we get t plus 2t cubed dt. Okay, this isn't so bad. This is t squared over 2 plus t to the 4 over 2 evaluated at 1 and 0. And then I sub in, I do the plug-in, and I get a half plus a half, and this is 1. Again, that's positive, is what we expected. So that's good. Remember, it's just along each point on the curve, you're integrating, you're taking that dot product and you're adding it all up. So if you're adding up a bunch of positive numbers, you should get a positive summation. That's kind of the main idea. Okay, and we're going to do one more example. And I'm going to move the page in a second, and we're going to go back to the rotational vector field. Our two best friends are our radial one. That's the one that we did here. I've drawn in green, and the previous one, which is the rotational vector field, the one given right there with the negative y comma x. All right, so we're going to go back to the negative y comma x. This is example 3. Okay, am I recording? Actually, that would be crazy if I weren't. Yes, I am. Okay. All right, let's do V is our beloved rotational vector field. And C in this case is the oriented, it's the oriented this counterclockwise oriented ellipse with, I'm going to call them vertices. This is the wrong word, at plus or minus 2, 0, plus or minus, and then 0, plus or minus 1. So I'll draw the picture here really quickly. So here are the axes of the ellipse, and we are traversing it in a counterclockwise fashion. If you ever change the direction, if you ever change the orientation of any of these curves, and you want to do a line integral, it actually affects the net value by flipping the sign, which is something to keep in mind. Which is because at each point you've changed all your angles either from acute to obtuse or reverse. So at each point you're integrating the negative function. Okay. And I'll draw the vector field here. And as I draw it, can people guess what they expect the net value to be? Positive, negative, or 0? Anybody have any guesses? My red arrows fighting or going along with my green? I'll get something. Oh, I'm seeing some positive. Yeah. Okay. Yeah. Again, we expect it to be positive. So we expect the integral, the circulation integral, to be positive. Because again, you zoom in at any point and you've got acute angles forming. Okay, good. And so we need a parameterization. And I'll say one thing. I'll say that C is actually today our first example of, this is an example of a closed oriented curve. Meaning it doesn't have endpoints. Like the past two examples, this had an endpoint and an endpoint. These were paths. This had an endpoint and an endpoint. These were paths. Over here, we've got a loop, so no endpoints. It starts where it stops. And this is more and more of our examples will be more and more like closed curves. All right, so I'll tell you the parameterization really quick. It's going to look like a sine cosine sine business, but I want it to be thicker in the x direction. So I literally just got to multiply my x component by 2. So my r of t is going to be double cosine, 2 cosine of t, comma sine of t. And my t is going to go from 0 to 2 pi. And so let's just look at some data. This tells me r prime of t is negative 2 sine of t, comma cosine of t. And let's figure out what v of x of t, comma y of t is, because this is an ingredient that we will need to use in our integral soup. Let's see. Well, I got to plug in my x where I see x and plug in my y where I see y. So I've got negative y, and y is sine of t. And I got to flip over my x. So I've got 2 cosine of t. Okay, so these are basically all the ingredients we'll need to set up the integral. So let's set it up. So we're doing c v dot t ds is equal to, okay, we do 0 to 2 pi. We do v of x, no, x of t, y of t. We dot that with our r prime of t. We've got ds. So this is the integral from 0 to 2 pi of, okay, we've got negative sine, 2 cosine, dotted with negative 2 sine, comma, cosine. And if I figure this out, I'm doing the integral. Okay, what happens? I get 2 sine squared of t, the negatives happen, plus 2 cosine squared of t dt, which gives me 2 times the integral of 0 to 2 pi times 1 dt, and this is just equal to 2 times 2 pi, which is positive, and which is what we had anticipated prior to setting up this integral. I would encourage you always to, whenever you're doing a problem, be it a test, on the final or on homework, draw the thing out first if you can, and then just see if you can guesstimate if you got the right answer at the end of the day. Sometimes it won't be as easy as these ones. Okay, so we've got 20 minutes left, and I would like to use this to talk about Stokes' theorem. Okay, so the sad part about this is that, so let's go, so now we're doing 6.4, and in your textbook, they will call this Green's theorem, but it's just a version of Stokes' theorem. So this is Stokes' theorem, and this is one of the first fundamental theorems of calculus that you'll see in higher dimensional calculus. And so, okay. So in the textbook, this is called Green's theorem. And you might hear other people call it Green's theorem, but I decided to call it Stokes' theorem because it's it really is. It's not important. I'm not going to bother you all with this, but I should tell you that the sad thing is that we've lost a week of school, and what I would have done had we not lost a week of school is this stuff, this circulation integral work. I would have given this a full class treatment worth of discussion. And so at this point, by the time we get to Stokes' theorem, what you would have had is an appreciation for maybe how difficult or what a line integral is, what a circulation integral truly is, because Stokes' theorem gives you a different way to compute it without having to parameterize a curve. So we'll just jump right in. I'll tell you the theorem. So let V be some vector field defined on a region R in the plane. So think of this, you've got some region in the plane. This is X, Y. That's R. And all over R, you've got some vector field. I guess I've been doing that in green. Something like this. Okay. You got some vector field. And then the R is the solid region. Okay. Then let C be the boundary, which is the edge of R oriented counterclockwise. So in this case, that solid region has an edge, and that is traced out by a curve, and we'll call that C. So this is C right here. Okay. It's very important that V is defined on the entire region. So there's no dividing by 0 that's happening. We'll talk about that later. That is actually an important point. So let C be the boundary of R oriented counterclockwise. So Stokes' theorem guarantees the following equality. So it's an equality of two integrals. On the left-hand side, I'm going to write a single integral. This is a circulation integral. So it's V dot T ds C. So this is the accumulate. I'm going to zoom in for a sec. This is the accumulation as you run along R, as you dot it with the green vector field that's present right there. Okay. There's a different way you can compute that integral. You can actually do a double integral over the solid region R. Double integrals are stuff that we've done in the second third of the class prior to midterm 2. And what function do you have to integrate? Well, you have to integrate the curl of v. This is an amazing theorem. So it's like, say you have, say you get a test question or a midterm question or a web work question, and they ask you to compute a really, really difficult closed curve circulation integral, and you don't want to parameterize the thing. Maybe you don't know how to parameterize the thing. Well, you can shift to the left, to the right-hand side, and you can say, well, maybe this is an easier integral to do. So let me give an example. So let me show you this in action, because you're really not going to have an appreciation for how cool this is until you start working with it more and more and more. So let's do an example. Let's do R, and I'm going to bounce off that previous example right here. So we're going to use everything we did in the previous problem. So I'm going to let R be the inside of the ellipse from before. Okay, so I'm gonna kind of draw it small. So this is R right here. It's wider than it is tall. That's my R. And so I want to remind you of some facts. So this means that C given by 2 cosine of t sine of t, which was the parameterization, I should call that R to be consistent. Exactly what we did in the previous problem for t between 0 and 2 pi, this defines the boundary. So this describes the boundary or edge of R. And we've got that going right here in red. And I'd like to remind you that the curl of v, so we're going to be doing, we've computed for this example on the previous page, we've done the left-hand side. What I want to do is compute the right-hand side. I want to show you that they're the same number. And the idea is that Stokes' theorem says that that isn't an accident, that always happens. But I want to show you this result in action. So I want to remind you that the curl of the rotational vector field, we did this on Monday, negative y comma x. This is exactly 2. We computed this on Monday. And that's how we said that this vector field was not a conservative vector field. Okay, so we've got that going on. And I would like to give you a little fact, is that the area of an ellipse with axes, with axis lengths like A and B is equal to AB times pi. This is a generalization of pi r squared, because a circle is technically just an ellipse with A equals B. So this means the area of R is 1 times 2 times 2 pi, which is 4 pi. Nope, that's wrong. That was wrong. Back. 1 times 2 times pi, which is 2 pi. So I'm going to do this left integral up here. So the double integral of curl over my ellipse R dA, curl of V dA is the double integral over my region. And we said it was constant 2 dA. This is 2 times the double integral of 1 dA over R, which is twice the area of R. And I've just said that that is 2 times 2 pi. And that agrees with, this is also equal to the single integral of V dot T ds. So we got that from the previous page. And Stokes' theorem says, so Stokes says this is not an accident, not a coincidence. Okay, that basically this integral happens to equal this integral. Okay, we'll do another example. Okay. All right. So this is a fun one. So let's do an example of using Stokes' theorem to make our lives easier. Using Stokes' theorem to make our lives easier. Okay, so I just cooked up some wild vector field. V of xy is xy squared comma y to the 5. I made this example last night. I've got no idea how it looks. It's just some mess. And I'm going to let C is the box or rectangle oriented counterclockwise. Okay, so I'm going to draw it in the plane. It's going to have like 4 corners, but that's okay. So this is like C1, C2, C3, and C4. I think I set this up as 1 and 2, 1 and 2 or something like this. I just made up some curve C. I guess I've been doing that in red. So that's my C. So I'm going to say C is basically C1 plus C2 plus C3 plus C4. It's got 4 components, but it's a closed curve, and it bounds this interior region R. Okay, so the problem might say compute the circulation integral as you move along that curve, along that red box. And you're like, okay, if I really want to do this, what do I have to do? I've got to parameterize. I'm going to zoom in for a second. I've got to parameterize this thing, do an integral. Got to parameterize this thing, do an integral. This thing, do an integral, and this thing. That sounds like a lot of work, and we don't like doing lots of work. Even people who do lots of math, they like to avoid doing work if they have to. So instead, I'm going to say instead of setting up 4 parameterized segments, because 4 as in the accumulation you would get on each edge, you want to do it 4 times, and there's just no way to set it up in a nice way that does it with one parameterization. There's just no way you're going to be able to do that. So instead of setting up 4 parameterized segments, let's use Stokes' theorem. So the integral of C, the integral of this dot product, the work we're doing along the curve C, is, by Stokes' theorem, this double integral over the box of the curl of V dA. Okay, so let's compute the curl of V. So we're going to need to know the curl. Remember, this is a little 2x2 determinant. I got my little derivative operators up here. And this is one way to set it up. This is xy squared, y to the 5. And I think I did this thing, like the Minnesota Vikings. Kind of did this thing. So in the yellow, I've got a derivative of, I'm taking a partial derivative of y to the 5th with respect to x, that's dead 0. And then I'm subtracting when I take a y derivative onto this piece, and I get 2xy. So that tells me my curl is just negative 2xy. And so now we're looking at the integral of negative 2xy over my square. But that square is really easy to describe. That's 1 to 2, 1 to 2, isn't it? 1 to 2, 1 to 2, dx dy. And now this is totally doable. This is a totally fair integral. I guess I'll do the x first. So I'm going to pull that negative 2. Well, yeah, I'm doing 1 to 2 negative yx squared evaluated at 2 and 1 dy, which is 1 to 2 For y minus y dy, and that's negative 3 halves y squared 2 and 1. Well, you can figure out that number. I don't know what it is. Well, we can figure it out actually. It's going to be negative 6 minus negative 3 halves. I think it's something like that. I don't know. I didn't do. I changed it just now. I changed it on my paper. I think I had 3 and 4 up here. Changed it to 1 and 2. But basically, the idea is that this double integral was much easier to do. We didn't have to parameterize crap. We didn't have to do those 4 edges, and that's the power of Stokes' theorem. Okay. I've got one last question. I think I can fit in the last 5 minutes, unless anybody has a question. And like I said, it's okay if Stokes' theorem doesn't immediately feel like this powerful, beautiful, amazing tool. It's like not intuitive. So Austin says if we define our function in a different coordinate scheme like polar. Yes. Austin asked a good question. So this question was really good to do in we found the function we had to integrate, and we knew which region we had to integrate over. So if the region were a semicircle, maybe we would have flipped everything to polar. That's good. But at the end of the day, right, it's a function of 2 variables over a solid region. And then by now, I know all of you can do something like that. Pick your coordinate system, pick your poison. Yeah, you're right. You could totally have done this in any coordinate system. That's good. Great question. And then let me think. Okay, I was saying that you might not have an appreciation for why this theorem is so cool. I just hope that in the coming weeks you'll gain an appreciation. So let me do something really fast. So the last one is let C be the curve, the counterclockwise curve given by the following. Okay, I just made something wacky up. So it again has 4 components. This is C1, C2, C3, and C4. All right. And so up here, this one is given by y equals x squared minus 2x plus 1. This is y equals x squared plus 2x plus 1. Y equals negative 1 minus x. Y equals negative 1 plus x. Really, those purple pieces don't mean so much. I'll promise. So, and then I'm going to say V is our radial vector field, x, y. So V is the one that comes out straight like this. And so the problem says compute the work integral along that full along that full outward curve of v dot my tangent vector, the work that I do at each point along the curve. I'm integrating with respect to s, and you can set up the 4 parameterized segments. That's really going to suck, and you might even get integrals that aren't doable. You probably will, but it's going to be just an absolute headache. Or you can use Stokes' theorem and say that this is a double integral over, I'm just going to call this inside region R, of the curl of V dA. But let's check out something really cool. Let's the curl of the radial vector field we computed to be 0. This is because you're doing x, y, x, y. When you hit this, you get a 0 derivative, and this gives you a 0 derivative. And so you're doing a double integral of 0, and that whole thing is just 0. Is R closed? Yes, R closed. Yeah, sorry. Yeah, sorry. That was a really good question. That's a really good question. So the full answer is 0, and you didn't even need to bat an eye. And we're going to get more of an intuition for why this is the case. We're going to play around with this a lot more. But and I guess the most important thing to notice is that in these last three examples that we did, the vector field, we never did any sort of dividing by zero. So here we had the rotational vector field, no domain issues. Here we had some vector field, but we didn't have dividing by zero. And over here, we also had a vector field that didn't divide by zero. A vector field where you would have to watch out for is something that I mentioned also at the end of class. I know I'm out of time, so you can leave, but I just want to say you would want to be careful if you saw something like this. This has a domain issue at the origin, and we're going to see that that's actually a really, really, really big deal. This is going to be a super big learning tool from us, but you can't plug in the origin at that point because you divide by zero. Okay, so I will turn off the recording now.